Okay, now we come to a demonstration. We actually do this experiment in our physics classes. It's called the moment of inertia experiment, and I could do a quick demo about it. So basically we have a rotating shaft like this, and we rotate we wrap the string around the middle axle, and then the string wraps around and comes over the pulley, and we hang a weight here. I can use 50 grams for that weight, 50 grams or 100 grams, depending on what I want to do. Okay, and then I can put any other object on top of the shaft. So the types of objects that I'm going to put is a solid disc. I've already, to speed up the experiment, I've already measured the mass of the solid disc, 1,435 grams, and its radius is 22.6 centimeters. I'm going to use the book that I used in the earlier demo, right? And it's going to be, the mass is 1,384 grams, 26 centimeters was its length, and 18 centimeters was the width. And then I have a sphere whose mass is 509 grams, radius 2.5 centimeters, and then I have a hollow cylinder, mass is 607 grams, radius is 15 centimeters. So then the physics of this goes like this. You have a hanging weight here, and the weight accelerates at a rate of a. So you have mg minus the tension is equal to ma, right? And then you have the torques on whatever you put here. The torques is equal to the moment of inertia of that object times its alpha, right? Now the torque is going to equal to what? Since the tension is wrapped around the middle pulley, it's the radius of the pulley. So I'm going to have to measure the radius of that axle, right? This middle axle. So it's going to be the tension in the string times the radius of that axle. So T times R, that's equal to moment of inertia times, and then alpha is the angular acceleration of the object, right? And then we know that the tangential acceleration at the rim of the object is equal to the alpha times r. And then the tangential acceleration at the rim of that axle should equal to the same as the acceleration of the falling object, since the system is accelerating together, right? So A tangential is equal to A, and then I can say alpha is equal to A over r. So I put here A over r, then I'm going to say, the rest of it is algebra. So I'm just going to say the tension in the string is equal to I, A over r squared. Substitute that into the tension for the falling object. I have mg minus I, A over r squared is ma, right? Then I have here, I just move this over to the right side, and then I bring this to this side. So I have here mg minus a, and then the r squared goes over to the top, and then the a comes down. This is the experimental moment of inertia of any object, right? So interestingly, the experimental moment of inertia of any object that you place here does not really depend on the mass of that object and on the radius of that object. This is the way to calculate the experimental moment of inertia of any object. So all I need to know is what I was hanging here, the mass that I was placing. Then I multiply it by the radius of the axle where I had wrapped it, and then I square that radius. Then I subtract the acceleration of gravity, 9.8, minus the acceleration of whatever the system that accelerated here, right? So since the height of the falling object is h, I can say here, we have here the x final is equal to x initial plus v initial t plus half at squared, right? V initial is going to be 0 because I'm going to let go of the object the same time I start the timer. So my V initial is going to be 0. So then my A is going to equal twice the distance that it travels divided by the time squared. That's the experimental acceleration. And the distance that it travels is just simply is equal to the h, the height h of the falling object, right? So we take twice the height, so divided by the time squared. That gives us the acceleration, and I put that acceleration here, and I put it here, and I get the experimental moment of inertia of that shape. Then we can compare to the theoretical moment of inertia of that shape as given by the theory section, right? So let's do one object at a time. The first one I'm going to do is the solid disk, and then you'll see this experiment run, right? Okay, so you can see here that the top of the table is 87 centimeters from the ground, and then this is the ground. Right, so I'm going to let the weight fall from 87 centimeters each time consistently. And I've got here the pulley, and then I've got here the shaft. And I've got here the axle where the string is wrapped, and I've already measured the radius of the axle, which is 1.3 centimeters. So then okay, so now I've got the start stopwatch started. And then this thing is falling. Okay, let's see what the solid cylinder will come out to. "15.13 seconds. Okay, now I've got the sphere sitting on the disc. And then I'm going to run the same experiment with the same height. It's going to be probably, the time is going to be longer than 15.13 seconds. The solid disc took 15.13 seconds, so this one is going to take longer because of the weight of the sphere and wherever it is sitting. And plus, I'm going to have to measure the distance between the center of the groove and the middle of the disc so that I can use the parallel axis theorem. 5 seconds, and the weight is falling. "19.96 seconds. Okay, now I've got the hollow cylinder taped to the disc, and I'm going to do the same thing. Let go of the weight, and then count the time. Okay, it's falling. "16.74. And now for the book, I could put it either the center of the book at the center of the disc, or I can put it at the edge, or I could even put it at a corner. The corner it's going to fall. I can put it here at an edge. I could put it at an edge at one of the sides so that I could also practice the parallel axis theorem. And now I'm going to tape it down and then run the experiment that way. Okay, so I've got it taped at the side edge right here. So I'm going to have to shift from the center of the book all the way to the side. Okay, now the book is rotating and the weight is falling. Let's see what it will come out to. "28.2 seconds. So, okay, now I've got all the times recorded. The solid disc was, of course, the quickest, 15.13 seconds. The sphere was 19.96. The hollow cylinder, 16.74. And then the book was 28.2 seconds. One correction I have to make, that the radius of the solid disc is actually half of this. This was the diameter. So half of 22.6 is going to be 11.3 centimeters, and then half of 15 is going to be 7.5. So this was also the diameter of the hollow cylinder, so 7.5 centimeters. Okay, so then using this equation, I'm going to first calculate the experimental moment of inertia of just the solid disc, right? And then compare, also I measured the radius of the axle to be 1.3, so that's for all my calculations, that's the same radius that I'm going to use, 1.3 centimeters, okay? Minus the A divided by the A. So I have to calculate what the A is. What is the A? 2h over t squared. Okay, what was my h? My h was 87 centimeters. 87 centimeters, and you saw that in the video earlier, and that's always the h that I'm going to constantly be using. So my acceleration is going to be twice the 87 centimeters, so let's write that there. 87 centimeters, which is going to be 0.87 meters. So it's going to be 2 times 0.87, 2 times 0.87 divided by the time, and then so for the solid disc we got 15.13, and then squared. So that's going to tell me what the acceleration is. Okay. So that's going to be the experimental moment of inertia of just the solid disk. Now, what's the theoretical moment of inertia of the solid disk? Right? The theoretical moment of inertia of a solid disk, where the mass is distributed throughout the disk, is going to be, I theory, is going to be 1/2 mr squared. This one depends on the mass of the disk, the theoretical moment of inertia, and then the radius of the disk squared. So I'm going to have here 1/2. Mass of the disk is 1435 grams, so change that to kilogram. You're going to have here 1.435. And then the radius of the disk, change that to meters, so it's going to be 0.113, and then square that. So I theoretical is going to be, this one is 10.89. The experimental moment of inertia is 10.89 times 10 to the minus 3. Usually the experimental moment of inertia will come out bigger because the friction on the axle, when it's rotating, the friction on the axle and the friction in the pulleys is going to slow the system down more than it should, right? And it's going to make the object look like it's harder to rotate than it actually is. So I do expect that the experimental moment of inertia is going to usually come out larger. So the way to do this would be to do many, many runs to average out that and then get a % error from the expected result, right? So then my % error will be error, okay? So again, it's hard to do this by myself as I'm illustrating this to you, so you would need a couple lab partners, right? Run this many, many multiple times and then compare the experimental to the theoretical and then get a result from that, right? Okay, so now let's do, keep this number handy, the moment of inertia, the experimental moment of inertia of just the disk, and I'm going to subtract that from all the other ones, right? Because when I ran the book, and I ran the sphere and I ran the hollow cylinder, they were all sitting on top of the disk, right? So the result that I get will include the experimental moment of inertia of the disk, so I'm going to have to subtract that number from all of them, right? So then, here 9.8 minus 0.0022, so the acceleration is less than when the solid disk was there by itself, right? It should be less because the book is heavy, right? Then you're going to divide by 0.0022. Then I'm going to subtract from there 1.089 times 10 to the minus 2, right? Minus 1.089. Let's just round this to 1.09 to make it easier. 1.09 times 10 to the minus 2. And then I experimental is going to be equal to, okay, of just the book, right? I subtracted the solid disks from the book. So now how do we calculate the theoretical? Okay, so then you're going to have here I theoretical. Well, the theoretical moment of inertia of a book, of a rectangular object around its center, right, around its middle, is going to be 1/12 times its mass times length squared plus width squared, plus the fact that I had it being rotated around the edge, right, I have to shift it. So I have to shift it by half of the width, right? So you're going to do plus m times w over 2 squared. Because the shift amount from here to here is w over 2, right? So w over 2 quantity squared. So I theoretical is going to be 1/12. This one actually comes out pretty close. I experimental comes out larger again, as I expected because of the friction, right? But it's actually pretty close. It's actually closer than this result. So 2.67 minus 2.27. So percent-wise, it's still pretty big, but the numbers are pretty close. So within the fact that I didn't time it that often and I was just by myself, and then the friction, the results are actually pretty good. Now let's do the sphere and then the hollow cylinder. The hollow cylinder, the experimental hollow cylinder, again, subtract from that the I experimental of just the disk, right? So minus 1.09 times 10 to the minus 2. I experimental of just the cylinder, the hollow cylinder, right? So that's 2.4 times 10 to the minus 3. So now let's calculate what the theoretical moment of inertia of the hollow cylinder is, right? So since the hollow cylinder, all of the weight is concentrated on the outside, the moment of inertia is just going to be its mass times its radius squared. Mass times its radius squared. Right? So actually, you can see here that this time the experimental moment of inertia came out to be smaller, 2.40 times 10 to the minus 3. So you could have anomalies like that happening because of timing error or all the other kinds of stuff. I might have let go of the cylinder before I started my stopwatch. I might not have done it at the same time. So again, the experimental came out smaller, but it is still within reasonable error again. So the percent error is going to be, okay. So the last one left to do is the sphere, right? So the sphere 8 times 10 to the minus 2. Okay? That is for the sphere. So then what's the theoretical moment of inertia of a sphere? Well, if the sphere is a solid sphere, which in this case it was, solid sphere, then the moment of inertia around its center, right, is going to be equal to 2/5 mr squared. But the sphere was not rotating around its center, it was off-center. So it was rotating around the center of the disk, right? So we need to use the parallel axis theorem to shift it, just like we shifted from the center of the book to the edge of the book, right? So we need to do plus md squared, and then the d is the distance between the center of that groove where it was sitting on and the middle of the disk, right? So that we're going to measure that distance now. Okay, that distance is 5.75 centimeters. The distance of the shift, 5.75 centimeters. So then I'm going to say the moment of inertia of the sphere is going to be 2/5. The mass of the sphere is going to be 1.81 times 10 to the minus 3 kilogram meter squared. This one, 1.88 times 10 to the minus 2, 1.81 times 10 to the minus 3. This is the one that I am most of. When I did the timing, I kind of could sense already that my time was probably up 19.96 seconds. It seemed like it was bigger than it seemed like it was too large of a time. It was too much larger than the hollow cylinder, which was 16.74. I already got the feeling that maybe I had a bad run. So again, in order to do this, you need to do this multiple times, 10, 15, 20 times. And then if you have an anomalous run, you don't accept that run, right? Maybe you, when you were holding it and you let go, it didn't really get started right away. Maybe you gave it a push in the opposite direction. So again, the timing was a little bit off. So what ended up happening, the I experimental makes it look like it's a lot larger than I theoretical, right? And my percent error is going to be large. So if I subtract this minus this, I'm probably going to get 100% error or something like that. I am 90% off. So you would see, I would probably repeat that experiment and see if that time was way off, or is that a consistent time? Is there maybe too much friction happening or what? But I'm suspecting, my suspicion is that the time, that it is actually just an anomalous run, that it's a bad run, okay? So you can see here, from this experiment, this is a theoretical, this is an experimental way of calculating the moment of inertia of any object. I can put any object here on top of the disk that I want. I could even put an irregularly shaped object, right, and then do the run, and then compare with the theoretical result, which I get by integrating. So you can put any kind of object on this and get its experimental moment of inertia and then compare it to its theoretical, okay? Thank you very much.